Lesson 4.6 deals with what we call logarithmic functions. In order to talk about logarithmic functions, we actually need to start with talking about exponential functions. So below here we have y equals 2 to the x. It's an exponential function. It goes through 0, 1, 2, 1, 2, negative 1 half, 2, 4. So there is the exponential functions y equals 2 to the x. To graph the inverse, it's a reflection over the y equals x line. And another thing we can think is we want to switch all of our x and y values. So here's 4 of the points on y equals 2 to the x, and what we want to do is we want to graph, we want to switch the x and y values. So let's start up here with this 2, 4. Well, what would that go to? That would go to 4, 2. So over 4 up 2. And then this one, that's going to go to 2, 1. So remember, to find the inverse, we just switch the x and y values. So there's the 0.21. This, we switch the values and we get 1, 0. And the last one, this will be 1 half, negative 1. That's that point. Also, notice we had a horizontal asymptote at y equals 0. Well, if we switch our x's and y's, we'll, instead of having a horizontal asymptote at y equals 0, we'll actually have a vertical asymptote at x equals 0. And so we can see that the graph of the inverse would look like this. Now, up until now, we don't really have an inverse of exponential. So to find the inverse, we would switch x and y. And then we would try to solve for y. Well, we don't really have a way to solve for y here. And so what we end up doing is we have this new function, or this new idea called logarithms, and they are going to be the inverses of exponentials. So logarithmic function, here's how we write it. F of x equals log base a of x, that's how we say it, where a is greater than 0, so it can't be negative, so the base can't be negative. And on top of that, you also a cannot be 1, and x has to be greater than 0. So also this can't be negative. It can be 0, but it can't be 0. It has to be greater than 0. It is the inverse of the exponential function f of x equals a to the x. So it's the inverse of something like we just did. We just graphed y equals 2 to the x. And so the inverse would be y equals log base 2 of x. Equations can be changed from logarithmic form to exponential form and vice versa. And here's how we do that. Here's a logarithmic function, our third bullet point here. It says y equals log base a of x. We can switch forms and we can switch to exponential form. And what we can think is the base of our logarithm is the base of our exponent. So a to the y power is equal to x. Or sometimes we just write x equals a to the y. It is very helpful to be able to convert from one to the other, and so we use this idea right here. I have an arrow going to the right here, but we can have an arrow going to the left as well. All right, so let's practice this a bit. A couple examples. Write log base 4 of 64 equals y in exponential form. We are going to use this idea right here. So y, now notice we have the y on opposite sides, so not a big deal. So remember the base of our logarithm is the base of our exponent, so 4 to the y power equals 64. So we were able to convert that into exponential form. Next one, we have exponential form and we want to convert to log form. So the base of the logarithm is the base of the exponent, and we can say that vice versa. The base of the exponent, 3, is the base of the logarithm, so log base 3 of the part that's on the other side of 1 over 243 equals -5. So those two examples show you can switch forms. We'll be practicing that more in our assignment. This last little one here says prove log base a of 1 is equal to 0 for all a greater than 0 with a not being equal to 1. This is actually pretty easy to show. We're going to start with our logarithm here. And what we're going to do is we're going to just change forms. So the base of the logarithm is the base of the exponent. It's a pretty sad looking a there. So a to the 0 power equals 1. And we know that to be true from our rules for exponents, that anything to the 0 power is equal to 1. So that was a really easy thing to prove. Just change forms and go back to a property we know from before. Now there are two types of logarithms that are that show up often, and so we're going to talk about those. First, we say the common logarithm, a logarithm with a base of 10. And so we use a base 10 in our math system. We have 10 digits, 0 through 9. So that's very common. The base of a common log is not usually written. So we don't usually write base 10. It says so in the equation log, look, no base written, log of 100 equals 2, we assume the base is 10. And so if no base is written, we assume the base is 10. There's a button on your calculator, LOG, the log button, and so we'll use that. And then over here we also have natural logarithms. Natural logarithms have a base of e. We haven't done a lot with the number e yet, but it will come up. The base of the natural logarithm is also not usually written. So what do? We already have one over here where we don't write anything. Log of 100 equals 2. So what we do is we use ln. So logarithm and natural. So ln to indicate natural log. Log base e of 7 is actually, it's easier to write. What we normally do is write natural log of 7. Natural logs can be found on the calculator. Use the ln button, the natural log button. All right, we have a couple examples here. Find log of 48. Well, there's no base written, so that's the understood log base 10. So what we'll do is we'll bring up a calculator here, clear what's there, and we want to do log of 48. So it is the fourth button on the left side from the top, log of 48. And we get that as 1.68. So this is going to be equal to approximately 1.68. So that's our answer. Now realize that means, so we have log base 10 of 48 is approximately equal to 1.68. I'm doing a little extra here. This just means 10 to the 1.68 is equal to 48. So just getting a deeper understanding of what that means. The next one, we want natural log. So we have the natural log button of 48. And that is approximately equal to 3.87. And again, if we thought through that, that would mean e to the 3.87 is approximately equal to 48. All right, so that's kind of the introduction of logarithms.